Welcome to the course on an introduction to information theory. So this is our last lecture, so I thought why not solve some problems related to information theory. So we are going to devote this session to some problem solving. So the first problem that we are going to solve is as follows. So prove that entropy is the only function that satisfies the 4 conditions for information measure. And what are those 4 conditions? So these are given in the form of axioms. So assume we have a random source X that consists of m elements with probabilities given by Pi. So axiom 1 says if all the probabilities are equal, then the entropy function or measure of information should be monotonically increasing function of m. The second axiom says for 2 independent sources x and y, where x has m elements and y has l elements, then information measure fml should be of the form fm plus fl. Third axiom is what we call grouping axiom. So uncertainty, basically P1, P2, P3, Pm can be written as entropy of P1, P2, Pr and Pr plus 1 to Pm plus P1, P2, Pr entropy of P1 divided by summation I1 to R Pi, P2 summation I going from 1 to R of Pi and Pr, and similarly plus Pr plus 1 Pr plus 2 up to Pm, and this is this branching entropy H of Pr plus 1 divided by summation of Pi where I goes from R plus 1 to M. Similarly P of R plus 2 divided by summation of Pi where I goes from R plus 1 to M up to P of M divided by summation of Pi where I goes from R plus 1 to M. So this is a grouping axiom, and the final axiom is basically this entropy function should be a continuous function of the probability set Pi. So we are interested to prove that entropy is the only function that will satisfy these 4 conditions for information measure. So we are going to show that only function that satisfies these axioms are of the form this. So let's first prove this. So that function for m raised to power k should be k times f of m for all positive integers m and k. We can use mathematical induction to prove this. So if m is a fixed integer, clearly for k equal to 1, that's true because f of m is equal to 1 times f of m, so that it holds true for m equal to 1. Let's say it holds for k equal to k minus 1, so we want to prove that it holds for k. So f of mk can be written as f of m into mk minus 1. Now this from axiom 2 can be written as f of m plus f of k minus 1. Now since this holds true for k minus 1, this would be given by k minus 1 f of m. So this when I add with f of m becomes k times f of m. So this also holds for k. So from mathematical induction we have shown that this holds for positive numbers, integers m and k. Now f of m is a form c log of m. So how do we show this? So let us take m equal to 1. So f of 1 is f of 1 dot 1, which from exam 2 can be written as f of 1 plus f of 1. So we have f of 1 equal to f of 1 plus f of 1. Now this holds true for only case when f of 1 is 0. Next, let m be a positive integer greater than 1 and let r be an arbitrarily positive integer. Now we choose r in such a way such that 2 raised to power r lies between two powers of m. Now what do we mean by that? So there is some k such that m raised to power k is less than equal to 2 raised to power r is less than equal to m raised to power k plus 1. Now we know from exam 1 that information measure should be an increasing, if all probabilities are same, it should be an increasing function of m. So then from there we get f of m k should be less than equal to f of 2r, and that should be less than f of m raised to power k plus 1. So this follows from exam 1. Now what is f mk? We just showed, if you recall, f of mk is given by this, right? So we can then write f of mk as k times f of m. We can write f of 2 raised to power r as r times f of 2, and f of m raised to power k plus 1 can be written as k plus 1 times f of m. Now if we take this and divide it by, if we divide all across by f of m times r, what we will get here is k by r is less than equal to f of 2 divided by f of m is less than k plus 1 divided by r. Now we know that logarithmic is also a monotonously increasing function. So if we take log of this, let's take log of this, what do we get? We get log of mk, that is less than equal to log of 2 raised to power r is less than log of m raised to power k plus 1. Now m raised to power k is k log m, log of 2 raised to r is r log 2, and this is k plus 1 times log of m. Now again we divide here by r times log of m. So if we divide this by r times log of m, what I get is k by r is less than equal to log 2 by log m is less than k plus 1 divided by r. So from here I got k by r is less than equal to f of 2 by f of m is less than k plus 1 divided by r, and here I got k by r is less than equal to log 2 by log m is less than k plus 1 divided by r. So from these two I can write that absolute difference between log of 2 by log of m minus f of 2 by f of m must be less than 1 by r. So this follows from this result and this result, this one, this result and this result. Okay. Now m is fixed, but we can make r very large. If we make r very large, this will 1 by r will become very small. So then this will tend to 0. As r goes to infinity, this will tend towards 0. Then basically what we will get is log of 2 by log of m is equal to f of 2 divided by f of m. Or in other words, f of m will be of the form c of log m, where c is f of 2 divided by log of 2. Now you can show the entropy of P1 minus P is of form this, where P is a rational number. So let us take P to be equal to R by S, where R and S are positive integers. Now from exam 1 we can write f of s like this, and from the branching exam we can write this entropy in this particular fashion. Now R by S is P, so this P, this is 1 minus P, this is P, again this is 1 minus P. So this will be we can write basically f of s of the form c log m. This will become of the form like this. So f of s is a form of c log s, f of r is a form c log of r. So what we get is this. Next, so from here we can write entropy of P and 1 minus P as, so if we bring all of them here, what we get is something of this form. Okay, and we get terms containing 1 minus P. If we do that, we get this of the form minus some constant times P log R by S. Now R by S, this is P, 1 minus P log of 1 minus R by S, so is 1 minus P. So what we get is, this is given by this. And this holds true for all P. This follows from the continuity exam. Now finally we are going to show that joint entropy of P1, P2, Pm can be written of the form minus C times summation Pi log Pi, where I goes from 1 to m. Now we are going to use mathematical induction to prove this. So we can see very easily this holds for m equal to 1. If m equal to 1, Pi is basically just 1, that it holds for m equal to 1. It also holds for m equal to 2. So let's see what happens when m is greater than 2. Now this joint entropy using grouping exam can be written as this plus this plus this. Now assuming this holds true for some k up to m minus 1, we will try to see whether this holds for k equal to m. So this can be written as, now we are making use of the grouping exam, and we can write this as minus C times this term plus this minus c times this term plus this plus pm, and this h of 1 was 0. So now we know that this term is given by this, because this holds for m minus 1, so this is the expression. Similarly, this expression comes here, okay, and this will be summation pi from I equal to 1 minus m, and the summation from p, and this will be p of this will be 0. So if you look at this term, essentially what we are going to get is of the form, this will be some c times pi log of pi, and there will be some term minus summation pi log pi. So this term basically comes out to be this. You can verify this. Now this, if you look at this term, you can take this common out, this cancel. So what we have is minus c summation pi log pi, and this is pm log pm. So this becomes this. So what we have shown is entropy function basically satisfies the axioms of information measure. The next question that we are going to solve is, so you are given 12 coins. Now you don't know whether they are counterfeit coins or not. So there might be some counterfeit coins. Now if there are counterfeit coins, the coin can be heavy or it can be lighter also. That also you don't know. Now so you are supposed to weigh these coins using a weighing balance. Okay, you are going to weigh these coins using a weighing balance, and in three weighing you will have to find out the counterfeit coin, number one. Second, you have to correctly declare whether the counterfeit coin is heavy or lighter. So how do we solve this? So you have 12 coins and there are 23 possibilities. So and we are denoting these possibilities. So this possibility corresponds to the coin, to the fact that one of these coins could be heavier or one of these coins could be lighter, or all coins are of equal weight. And we are denoting by these numbers these 23 possibilities. And we are going to write these numbers using ternary alphabet, -1, 0 and 1. So these 12 coins, I am just writing these 12 in the equivalent ternary notation. So 1 would be 1 times 3 raised to the power 0 plus 0 times 3 raised to the power 1 plus 0 times 3 raised to the power 2. Similarly, you can see this 7 is nothing but 1 minus 3 plus 9, that's 7. Okay, so I can write any number. Let's take 10. 10 I can write as 1 plus 9, that's 10. So that is 1 times 3 raised to the power 0 plus 1 times 3 raised to the power 2. Now, so I have written all of these 12 numbers in the ternary notation, -1, 0 and 1. Now if I sum up in each unit that corresponding to 30, 3 raised to power 1, 3 raised to power 2. If I sum them up, I get here 0, 2 and 8. Now what I do is I negate columns 9, 7, 9, 11 and 12. So what I did was, so 7 was 1 minus 1, 1. I made it minus 1, 1 and minus 1. Similarly 9 was 0, 0, 1. I made it 0, 0, minus 1. 11 was minus 1, 1, 1. I made it 1, minus 1, minus 1. And 12 was 0, 1, 1. I made it 0, minus 1, minus 1. Now by doing this, you can see here, when I sum up these numbers, I get 0. So this row, if I sum them up, I am getting 0. Here I was getting earlier also 0. But if you look at these two rows, earlier I was getting 2 and 8. But now, as a result of negating of these few columns, I am getting 0. Next, how am I going to weigh them? So I am going to place a coin n on the left pan if Ni is minus 1, and I am going to put it on the right pan if Ni is 1, and if Ni is 0, I am not going to put it in any pan. So for example, so you are going to weigh 3 times, first corresponding to this row, second time corresponding to this row, third time corresponding to this row. So when I am doing this weighing corresponding to this row, so I am going to put this in the right pan, I am going to put this in the left pan, I am going to put this in the right pan, going to put this in the left pan, going to put coin number 7 in the left pan, coin number 8 in the left pan, coin number 10 in the right pan, coin number 11 in the right pan. And the ones that you see which are 0, the coin number 3, coin number 6, coin number 9, coin number 10, 12, I am not going to put in any of the pan. This is for the first weighing. Similarly, for the second weighing, I am going to put coin number 2, 3, 4, 7 in right pan. I am going to put 5, 6, 11 and 12 in the left pan, and I am not going to put coin number 1, 8, 9 and 10. Likewise, for the third weighing, I am going to put coin number 5, 6, 8, 10 in the right pan, and coin number 7, 9, 11 and 12 in the left pan, while coin number 1, 2, 3, 4 are not put in any pan. Now, the claim I am making is the result of each weighing is, if the result of each weighing is minus 1, it means the left pan is heavier, and if the result of weighing is 1, it means the right pan is heavier, and if it is 0, then both the pans are of same weight. So what I am going to do is, when I weigh them and I find the left pan is heavier, I am going to give a number minus 1. And if the right pan is heavier, I am going to give number 1. And if both the pans are of same weight, I am going to give number 0. This is the result of my weighing. Now 3 weighings of the coin can give me the ternary representation of the index of the odd coin. How? If the expansion is same as the column of the matrix, then the coin is heavier, and if it is of opposite sign, then the coin is lighter. So what I am saying is, as a result of my weighing, when I give these numbering -1, 1 and 0 depending upon which pan is heavier, if that numbering comes out to be same as, if that expansion comes out to be same as a column of this modified matrix that I had, then the coin is heavier, and if it is of the opposite sign, then the coin is lighter. So let us check this result. Pick up any coin. Okay, let us see. We pick coin number 4, and let us see, this is heavier. Let us say coin number 4 is heavier. Now if coin number 4 is heavier, when we do this first weighing, what would you notice? Because this expansion is 1, so we would have put it in the right pan, and since coin number 4 is heavier, the right pan would have come out to be heavier. So the result of our outcome would have been 1. Similarly, for the second weighing corresponding to this row, if you look at coin, fourth coin, this is 1. So we would have put this coin in the right pan, and then again the outcome of our weighing would have been 1. In the final weighing, which is corresponding to the third weighing, since this is 0, we wouldn't have put this coin in our weighing, so we would have observed that both left and right pan are of same weight. So the result of an outcome of weighing would have been 1, 1, 0. Now if you compare 1, 1, 0 with the columns of this matrix, we see that this column corresponding to coin 4 has the same expansion, and as I said, so we are able to identify the odd coin is coin number 4, and since the expansion of this is same as expansion of column 4 in this matrix, the coin 4 is heavier, which it indeed was. Now let us take another example. Let us take coin number 10, and let us say this coin is lighter. Now if this coin is lighter, so in the first weighing this is 1, so we would have put it in the right pan. Now since this is a lighter coin, left would have come out as heavier, so result of first weighing would have been -1. Now in the second weighing, since the expansion corresponding to 10 here is 0, we wouldn't have put this coin anywhere. So result of our weighing would have been that both left and right pan are of equal weight. So then this result would have been 0. And finally for the third weighing, since this is 1 here, we would have put this coin in the right pan, so left pan would have come out as heavier. So this result of our outcome of weighing would have been -1 for the third weighing. Now look at, do we have any column of this matrix which has this expansion -1, 0, -1? We don't. But if you look at expansion for 10, if you multiply it by -1, you get this. So then we are able to identify that the coin number 10 is counterfeit, and we are also able to identify, because the expansion of 10 is 1, 0, 1. So and this is -1, 0, -1. So we are also able to identify that not only coin 10 is counterfeit, but it is of lighter weight. Okay, the next problem that we are going to solve is as follows. So we want to show that entropy of x0 given xn, it increases with n for a Markov chain. So if x0, x1, x2, xn forms a Markov chain, then we know x0, x1, x2, if they form a Markov chain, then from the data processing lemma, we know that mutual information between x0 and xn is less than mutual information between x0 and xn minus 1, because we know that further processing of data does not increase the mutual information. So then from the definition of mutual information, we can write this as uncertainty in x0 minus uncertainty in x0 given xn. Similarly, this we can write as uncertainty in x0 minus uncertainty in x0 given xn minus 1. So this is common. So what we get is minus of this is less than equal to minus of this. So then multiply by minus 1 both sides, we get entropy of x0 given xn is greater than equal to uncertainty in x0 given xn minus 1. So as n increases, you can see this entropy increases. The next question is, under what condition does uncertainty in x given g of y is same as uncertainty in x given y? So if uncertainty in x given g of y is same as uncertainty in x given y, then h of x minus h of x given gy can be written as h of x minus h of x given y, or in other words, the mutual information between x and gy is same as mutual information between x and y. Now we know x, y and g of y forms a Markov chain. Then mutual information between, from data processing lemma, we know mutual information between x and gy should be less than equal to mutual information between x and y. And here it's given it's equal. And when does the equality happen? The equality happens when x, gy and y also forms a Markov chain. So this result comes from the property of data processing lemma. So we know that this equality will happen if gx, gy and g also forms a Markov chain, and that is the general condition I am talking about, under which uncertainty in x given gy is equal to uncertainty in x given y. And there are many special cases, for example, g being 1 to 1, x and y independent, but the general condition is this. Okay. The next question is on proving whether a function is convex or concave. We want to show that mutual information is a convex function of p of y given x for a fixed p of x. And how are we going to prove that? So let p0 j by k and p1 j by k, where k varies from 0 to k minus 1 and j varies from 0 to j minus 1, be two arbitrary set of transition probabilities. We define p of jk as theta times p0 j given k minus 1 minus theta times p1 j given k for some theta which lies between 0 and 1. Now let I0, I1 and I be the average mutual information for these three sets of transition probabilities, namely P0, P1 and this Pj. Now we want to show or prove that mutual information is a convex function of p of y given x for a fixed p of x. So to prove it, we have to show that theta times I0 plus 1 minus theta times I1, that is greater than equal to this average mutual information corresponding to this transition probability. So let us consider P0 and P1 to be conditioned on some binary random variable z. So we have a binary random variable z which takes values 0 and 1, and P of 0 can be written as probability of y given x and z, where z is 0, and probability P of 1 can be written as probability P of y given xz, where z is plus 1. Let P of z being 0 is given by theta, so P of z being 1 will be 1 minus theta, and z is considered to be statistically independent of x. Now we want to show that mutual information is a convex function of p of y for a fixed p of x. So let us see. As I said, we have to prove this. We already showed that we are considering P0 and P1 as conditioned on this binary random variable z. So P0 can be written like this and P1 can be written like this. This is a diagram corresponding to that. To think of it, this x and y, they are conditioned. Probability of y given x is conditioned on probability of y given x and z, whether z is 0 or z is 1, and these are the channel transition probabilities. Now what is this term? P theta is nothing but P of z being 0, and I of 0 is corresponding to this transition probability P of 0, and 1 minus theta is the probability of P of z being 1, and this is a mutual information corresponding to transition probability P of 1. So this can be written as mutual information between x and y given z. Okay, and what about this? This is nothing but mutual information between x and y. So to prove that mutual information is a convex function of p of y given z for a fixed p of x, we will have to show that this relation holds. Now using chain rule, we can write mutual information between x and yz as mutual information between x and z and mutual information plus mutual information between x and y given z. Now if we apply chain rule in another way, we get this as mutual information between x and y plus mutual information between x and z given y. Now since x and z are statistically independent, mutual information between x and z will be 0. So this term will be 0. So then what we get is mutual information between x and y given z is equal to mutual information between x and y plus mutual information between x and z given y, and we know that mutual information is greater than equal to 0. So this shows that mutual information between x and y given z is greater than equal to mutual information between x and y. So we have proved that this relation holds, and hence we have proved that mutual information is a convex function of p of y given x for a given p of x. Now in this question you have been asked to design an optimal uniquely decodable code which is not a Huffman code. Now what are the properties? So here you have been given a source with source alphabets given by this, and the symbol probabilities are given by this. I forgot to mention, basically I mean which is not a binary Huffman code. Okay. Now what are the properties of a binary Huffman code? We know that there are no unused leaves, and the two least likely symbols, they differ in only 1 bit location. And when I say find an optimal uniquely decodable code, I want the expected code word length of this uniquely decodable code to be same as that of Huffman code. However, it's not an Huffman code. So how do we solve this? So first we are going to do is, we are going to create a Huffman code using these symbol probabilities. So you can see here two smallest symbols with probabilities are this 0.01 and 0.11. So I join them, get probability 0.2. Next, so I deactivate these nodes and activate this node. Now the two nodes with least probability at this time is this one which has probability 0.15 and this one which has probability 0.15. So I deactivate these nodes and this is probability 0.3. Next I have this as 0.3, this as 0.23, this one as 0.2 and this one as 0.27. So the two least likely active nodes are this one with probability 0.2 and this one with probability 0.23. So I deactivate these nodes. Now I have this node with probability 0.43. Now among the 3 nodes remaining, this one has probability 0.27 and this one has probability 0.3. I join them, so I get this as node has probability 0.57. I deactivate these nodes and finally I join this node and this node, and I get here this is probability, root has probability 1, and deactivate this. So if you now assign code words, you can assign 0 1 0 0 1 0 1 0 1 0 1 0 1. So what you will notice is, so this has code word 1 0, this is 1 0, this is 1 and then this is 0. This one has code word, let's see, 0, this one 0 and then 0 and 0. This one has 0 and then 1, 0 and 1. This has 0 and then 0 and then 1. So 0 0 1. This has 1 1 0 1 1 0 and this one has 1 1 and 1. So if you notice in the optimal Huffman coding for this source with these source probabilities, I have 4 code words of length 4 and I have 2 code words of length 2. And remember, the 2 least likely symbols, which are probability 0.09 and 0.11, they are differing only in 1 bit location. Correct? Now if I swap, these 2 code words are also having 3 bits. If I swap any one of them with For example, if I make this code word as 0.001 and I make it this one as 110, then it does not change the expected code word length. However, it is now no longer Huffman code. Why? Because now the least likely code word, this one has 000 and this one has 110. So two least likely code words are differing in two positions. So it's no longer a Huffman code. So this way you can solve this problem. This is a Huffman code, as I said, and if in case of Huffman code, two least likely code words differ only in the last bit. So if we interchange the code word for one of the source alphabet with probability 0.15 with the code word for source alphabet with 0.1, we still get a uniquely decodable code, and it is not Huffman code. In fact, we get a prefix free code, but it's not a Huffman code. One such example is this. Prove that, the next problem is, prove that for a binary Huffman code, if the most likely message symbol has probability greater than 2 by 5, then it is the only message symbol and it is the only message symbol with this probability, then that symbol must be assigned a code word of length 1. So what I am saying is, the most probable message symbol has probability greater than 2 by 5 and it is the only message symbol which has this probability. Then show that this symbol must be assigned a code word of length 1. Now we are going to use method of contradiction to prove this result. Now how does method of contradiction work? So we are going to assume that, let's say, this particular message symbol requires more than one length code word, and then later on we will show that this is not possible. So our initial assumption that this message symbol has code word of length greater than 1 is incorrect, and that's how we will prove it. So let us assume that code word length of the most probable message symbol is larger than 1. If that's the case, this is the kind of Huffman tree, binary Huffman tree you will get. So I'm just referring to this message symbol by with as Q1 here. So I have Q1, Q2, Q3, Q4. Now these probabilities Q1, Q2, Q3, Q4, they should add up to 1, right, because sum of probabilities at the root should be 1. So let's say I have at depth 2, this is how I have these probabilities Q1, Q2, Q3, Q4. Now consider two cases. In case 1, we consider that Q3 and Q4, their probability is more than Q1 and Q2. So what we are considering is that these probabilities are more than these probabilities. That's the first case. And the second case, we will assume these two probabilities are more than these probabilities. So if Q3 and Q4 are more than Q1 and Q2, and since Q1, that message symbol with probability 2 by 5 is there at Q1, so Q3 and Q4 must also be greater than 2 by 5. Now if we add up Q1 plus Q2 plus Q3 plus Q4, we get, because Q3 and Q4 are 2 by 5 and Q1 is also 2 by 5, so Q1 plus Q3 plus Q4 itself is greater than 6 by 5, which is not possible. So we cannot have this case 1. Now let's look at case 2. So here we assume Q1 and Q2 is greater than Q3 and Q4. Now we also have Q3 plus Q4 to be greater than Q1, otherwise we would have joined them. So Q1 plus Q3 plus Q4 is greater than Q1, which is greater than 2 by 5. Now since Q1 plus Q2 plus Q3 plus Q4 should add up to 1, what we get from here is, so 2 times Q1 plus Q2 is less than equal to 1. So 4 by 5 plus Q2 is less than equal to 1, or we get Q2 is less than 1 by 5. Now since Q1 and Q3 are greater than Q3 and Q4, Q3 plus Q4, if we add them up, they must be less than 2 times Q2. And what is Q2? In this case, Q2 is less than 1 by 5. So then if this condition holds, what we have shown is Q3 plus Q4 is less than 2 by 5. However, we have also said Q3 plus Q4 is greater than Q1, which is greater than 2 by 5. But here we are getting Q3 plus Q4 is less than 2 by 5. So this is contradicting, because from here we are getting condition that Q1 is less than 2 by 5, but we are given that Q1 has probability greater than 2 by 5. So hence this contradicts our assumption that the message symbol with probability 2 by 5 is assigned a code word of length greater than 1. So since we have considered all possible cases, so we know that it is not possible for a message symbol with probability greater than 2 by 5, and if that is the only message symbol with that probability, it is not possible for this message symbol to have a code word greater than length 1. So since the original assumption is false, so by method of contradiction we know that the code word length of this message symbol has to be 1. Finally, we just conclude with one example. So we have a Gaussian source with 0 mean, variance sigma square, and let the distortion measure be squared distance. So you have been asked to show that the optimal reproduction points for 1-bit quantizer is given by this, and the expected distortion for 1-bit quantizer is given by this expression. So this is a Gaussian distributed random variable, right? It's 0 mean Gaussian distributed random variable. Okay, so symmetric across around 0. Now with 1-bit quantizer, it is obvious that the reconstruction regions are, one is negative real axis and other is, so one is negative real axis, other is positive real axis. So to find out the optimal reproduction point, we need to find the centroid of these regions. So the reconstruction point is nothing but centroid of this negative half region or the positive half region, and they are symmetric, right? So if we consider, for example, the real axis, then the centroid points comes out to be, so this is integration from 0 to infinity 2 times exponential of minus x square by 2 sigma square divided by under root 2 pi sigma square, and this comes out to be sigma times under root 2 by pi. And similarly for the negative real axis, the centroid point will come out to be minus of sigma under root 2 by pi. Now to find out the expected distortion, so for the negative real axis, the reproduction point is minus sigma under root 2 by pi, whereas for the positive this is the reproduction point. So distortion is given by x minus of sigma under root 2 by pi, and since the distortion is squared error, so we take a square of this. This is the PDF of the source integrating from minus infinity to 0. Similarly, this is the centroid point for the positive real axis, so we integrate from 0 to infinity, and this is the PDF of the source. So by doing some algebraic manipulation, what we get finally is this, that the expected distortion is given by sigma square into pi minus 2 divided by pi. So with this we will conclude this lecture. Thank you.